Okay, hello everybody, good morning. So my name is William Zhang and I'm gonna be the tutor or the leader for this final review session. This is for Pure Science 1. Is everyone ready? Yeah? Okay. So the topic for today that I planned out was gonna be on using Dr. Znamski's URI packet. It's gonna be on tries, heaps, hash tables, some base conversions, bitwise operations, twos complements, and bitmass. We'll look at backtracking, and hopefully that will encompass all our time. If not, we can look at runtime analysis and recursion, and look at recursive relationships. And if any more time's over, we can look at other things that you have any questions on, any topics on. Okay? Sounds good? Okay. So first things first, let's look at tries. So questions to ask ourselves is, what are tries and when do we use tries? So tries usually have the structure. Okay? So we have a root, and then these tries usually have it's usually from A to Z, which is usually an array of pointers to our structures. Okay, usually the first array is at A, and the last index is at Z usually. Okay, so what's the big O runtime for insertion into a try? For worst case, we have to, if we're inserting strings, we have to go through all the letters in the string to insert it. So it's going to be big O K, where K is the length of the string. Okay? So the best case for insertion still, if we want to insert a string into our try, it's still going to be big O K, where again, K is the length of the string. And then for lookup, if we need to look up a string in our try, it's going to be big O K, because we have to go through all the letters in the string to find the string. But in the best case, if the string's not there, we can just say it's big O1 because the string's not there. For deletion, it's going to be the same thing as our lookup, where if we need to delete a string, we need to go through all the letters in the string. And for deletion, in the best case, if the word is not in our try, it's going to be big O1. Okay? Is everyone okay with that? Okay. So I came up with an example of showing how instruction looks like in a try. So the words already in the try is air, novel, and prospect. I want to insert the following words into the try, which are arid, novice, and Prozac. Okay? So to insert arid, we need to go down, traverse down our try, and find A, then look for R. If R's not there, we just plop it in there and say, like a wizard, we just make R there, and then we go down our traversal and keep plotting until we reach the end of our word. Okay? And that will be the searching for arid. So same for novice, we just keep going down the try and look for N, O, V, and we see that I's not there, so we just create an I node there. So then we go to I, C, then E. Okay, that's for novice. For Prozac, we do the same thing. P, R, O, S, then A, then I, then C. Okay, that's how we do insertion. So for deletion, we just look for the word, and then we delete it. We just scribble it out. Okay, so we create the node. We try to duplicate what we have here, but now we remove Prozac and prospect. So the P's are all gone because that's the only words in our P index. So prospect and Prozac. Okay. So we just do A for air, then arid, R, I, D. Then we do not the ends for novel. Wait, is this novel? It's not novel. This is a V. Whoops. Then for novice. Okay. Does that look good to you? Okay. So because Dr. Zemsky wants us to memorize our powers of 2, I sprinkle in bits of questions for asking us what's the power of. If you look at the bottom of the page, it asks us math surprise. The 2 to the 5th is what number? So if you know your powers of 2s, it's gonna be 32. Okay, it's gonna be helpful when you do your bitwise conversions and bitwise operations. Okay, so that's for trees. Does anyone have any questions on trees, or we're good on trees? You good? Okay. So let me just. So next topic is gonna be on heaps. Okay. Okay. Let me just get my bearings for a bit. Okay. So I've come up with a question on definition of a heap. What is a heap? And what properties do heap have? So since Dr. Zansky wants us to know, we're using mean heaps as our implementation of heaps. So for a mean heap, it's a binary tree that is something where the only level that is not filled up is the last level, and it's filled up from the left to the right with no gaps. So this definition is for a complete tree, complete binary tree. And also, the mean heap has a ordering property where every node has a value blank to all values in the subtrees. So for a min heap, it's going to be less than or equal to. For max heap, it's the opposite, where the value is greater than or equal to all values in the subtree. Okay? Does anyone see that? Does that look good? Okay. So for insertion into a mean heap, what's the worst case? For worst case, we have to traversal all the way up through our min heap. Because if we insert a small value in a min heap, we have to put that value into the root. So it's going to be order log of n, where n is the number of nodes in our min heap. For best case, it's going to be order 1, where the value we inserted is the largest value. So for delete min, worst case is also going to be order log of n, because if we delete the minimum number and we get a big number back, we have to push it down and percolate down log n times. Okay? And then if we do delete min and we find a small number, it's going to be ordered 1 for best case. Does that sound good? Okay. So let's trace through what insertion looks like if we insert 25, 10, and 125 into this pre-made min heap. Okay? So if we insert 25, it's gonna go, we have to insert it at the available, the rightmost available leaf node. Okay? So in 25, it should go about right here. This is the rightmost leaf node. Okay, so we show that here. We duplicate the already made min heap. I'm going to create 51. I'm going to copy this subtree. and put it here. But because we see that 33 is greater than 25, and because we need to fulfill this requirement that every node has a value less than or equal to all values in subtree, we have to call percolate up on 25 and move it up, okay? So it's going to look like this when we call percolate up. So 20, 25, and then 52, and 20, and 33. Close. Okay? So this is just the same thing as before. 50, 100, and 51. So that's what it looks like when we do insert 25. Okay? So now let's insert 10. Oh, you can't see that. Oh god. So, okay, so what I did here is that I insert 25 here, and I saw that 25 was less than its parent, so we call percolate up, and we move 25, we swapped 25 up and 33 down. Okay? So these are swapped. Okay. This is the result of the percolate operations. Okay, sounds good. So now let's do insert 10. So for 10, we look at the rightmost variable leaf node, and it's going to be here. So, okay, so we just put 10 in here. So let's put 10 in there and see what's up. So 10 goes here, that's 20, 50, 100, 51, and we have 10 here. Okay, so we can say, oh man, this doesn't look good. Okay, so we have 10 at the rightmost leaf node here, and then we should call percolate up and see if 10 is going to be a value less than its parent. If it is, we push it up and up until it's no longer a value that's less than its parent. Okay, so we call percolate up here and see that 100 is greater than 10, so we push it up here. We call percolate up on 10 here, and we see that 50 is greater than its child, then we call it push it here. Then we call it again and see that 20 is greater than 10, so we push up here. So our end result is going to look like this. 10 being a root node now, 20 gets pushed down, 50 gets pushed down, and 100 gets to the leaf now. And the right subtree is still unchanged. Okay, does that look good, everyone? Okay, so now after inserting 25, 10, we're going to insert 125 and see what that looks like. Okay. Okay. So if we insert at the variable rightmost node, it's going to be right here. That should be the spot. But we should call percolate up here and check that if the value of its parent is less than 125, we have to push up 125. If not, just leave it there. Okay, so we're going to create our heap again. And then we plop 125 here. Okay. Okay, so when we do call percolate up here, we see that 50 is less than 125, and our ordering property holds, so we don't need to push up 125, we can just leave it there. That's good enough. Okay, so in helping you remember what your powers of 2 are, what's the power of 2 to the 3? That's gonna be 8. Okay? Okay. So for our next agenda, we've done tries, we've done min heaps. We're gonna do hash tables. Okay? So for hash tables, what's the runtime of insertion and search retrieval? Best case and worst case. Okay? So when we insert into a hash table using linear probing, worst case is gonna be order n, where n is the number of items we were put in there. Okay? Because when we do insert, in the worst case, we hit all our previously inserted elements. And we keep hitting collisions. So in the worst case, we have to go to the last, the most, I guess, would say, the most. I want to say the most times to insert into the hash table. Okay. So for the best case, when we do linear probing and insertion, it's gonna be order 1, where the index that we've used to place the element is available for us to use. Okay. So again, the worst case for linear probing is order n, where we have to place the element, and if at the index where it's not available for us, it's already being used, we have to keep going one by one until we found a index that's available for us. Okay. So for search and retrieval, it's the same thing. Respectively, it's going to be the worst case order n, the best case order 1, where if the element at the original index in our hash function gives us, let's say, index 5, but index 5 is already being used, we can't use index 5, so we go to the next index, which is 6, and that's, if 6 is being used, we have to go to 7 and so forth until we find available spot to use. So for quadratic probing, it's gonna be the same thing. For worst case, it's order n, where we've collided with the elements we already seen before, and then we have to keep on increasing the I value for when we have to insert our element. Best case order 1, where the hash function gives us a good number, and the number of the index is not being used by any other element, and you can just insert it there. So same thing with inserting into a linear probing style. Quadratic probing uses order n as a worst case, and order 1 as a best case. Okay, but for separate trading, it's gonna be different. For separate trading, worst case it's gonna be ordered 1, because you just insert it at the head of the linked list. It's gonna be an order 1 operation. For best case, it's still best is order 1. Worst case for search and retrieval is order n, because we have to go through all our elements to find the element we want to find, if it's all in a linked list. So best case ordered 1. Okay. So is everyone fine with that? Okay, awesome. So for the next questions, I'm going to ask to trace through some insertions. So insert some elements into the hash table using the collision resolution policy that we've specified. The table is of size 10, so assume that to determine the hash value for a given input key, we calculate the hash value using this function. Okay. So for 3, the index to insert it at is going to be at 3 mod by the table size, which is 10. it's going to be 3. Okay, so we just plop 3 here. And then we go to the next element, which is 13. And we see that 13 mod by 10 is going to be 3. So we've hit here. We've got a collision, so we go to the next available index, which is 4. So 13 goes here. Then at 16, we mod by 10, it give us 6. So it's going to be here, 16. So for 18, we mod by 10, it gives us 8, which is at this spot here. Okay, so if we go 23, we mod by 10, it gives us the index to use is going to be 3, but 3 is already taken, so we've collided. We go to the next index, 13 is collided, and go to the next index, which is 5. So we put 23 at index 5. Okay, and then for the next element, 33, we go to the next. We use our hash function to find the index to use for 23. It's going to be 3, and then we go to 3. We said it's collided with a with 3, collided with 13. Go to the next index, collision at 23. Go next index, 16 is already at 6, and then 7 is our next available index to use. We put 23 here. Okay. So that's for linear probing. If you want to insert it, we see that if for assertion ordered 1, for best case where the index we have is free and available to use, but we see that for if we say insert, if we do insert 43 in there, we get 3 again. It's going to go through all these elements, which is the number of elements in our hash table, which is let's say the total number of elements in our hash table is n. We go through all n of these elements, and we find that the next spot is at 9. This is why it's called big O n for worst case. Okay. So now let's insert the elements into the hash table using quadratic probing to resolve collisions. Okay. So quadratic probing, we don't insert it linearly. We have to go off by we square the I index every time we found a collision. So let's see that happen here. Okay. So for 3, we use the same hash function to get our index. So 3 goes to 3. So it's already here. So 13 goes to 3 again. So you see that it's collided. Go to 0 squared, and 1 square is here. And then we go to 16 and see that it's here. Go to 18, that's here. And then we see 23 is collided. This is 0, 1, 2, 3, 4. 4 will be the next available index to use. Okay. Then for 23, it's going to be a 3 collided. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 will be, so index 2 will be here. That's if you want to insert our elements into the hash table using quadratic probing. Okay, that sound good? Does that look good? Okay, so now let's insert the elements into our hash table using separate chaining. For separate chaining, we want to insert into the hash table at the head of the linked list. There's a concept called temporal locality, where it says that data that's been used will be likely to be used again sooner. Okay, so since we are inserting at the head, it's better to go backwards, so we don't have to I want to say don't have to deal with making space for the head. Okay, so at 33 it's gonna be at 3, At 23, it's going to be at 3. So we just make a pointer to 23. Then at 18, we just plop it here. 16, put it here. For 13, it's going to be here. Then at 3, it's going to follow 13. Okay? So if we did insert it normally, starting at 3, we see that 3 is going to be the first element to be inserted, and 13 is going to be the next after 3, which is the head of the linked list. Then at 23, it's going to be here. 33 is here. So by inserting it backwards, we can safely insert into the hash table using separating. Okay. Okay. So there are 2 rules for if we want to use quadratic probing, so that it finds a empty space in our hash table without looping indefinitely. These 2 rules says that the hash table must be at least half empty, and that the size of the hash table must be a prime number. Okay, so be sure to know those rules in case you need to expand your hash table if you want to use quadratic probing to find a guaranteed empty space. Okay, so next part of 2 questions is going to ask you, what is 2 to the power of 10? 2 to the power of 10 is going to be 124. Okay. Okay. So does everyone understand hash tables? Is that clear? Is that good? Okay, awesome. So next topic to talk about is base conversions, bitwise operations, and 2's complement and bit mass. Okay. So let's talk about how to convert from base 4 to base 16. So there's 2 methods to use. We can use a long way, or we can use a shortcut. If you want to use a long way, we have to go to base 4 to base 10. Oops, base 10, then to base 16. So to do that, we take our number and divide it by the base. So if you want to go that route, this is a big number, so you won't, I don't think Optimus will allow you to use a calculator. So if you see a big number and you have to, that's right, 1, 2, 3, this is a 1. So best bet, if you see a big number and you need to do base conversions, we should use the shortcut. But to help us appreciate the shortcut, let's go to the long way first. Okay, so divide by 4. What that gave us? Well, let's see. So long division, we do it this way. So 3 divided by 4 is going to be 0. That's not good. We drop that to 2. It gives us, that's going to be 8. Then drop a 1 here. That's 1 doesn't go into 4. So we put 10 here. So let's go twice. 2 times 4 is 8. So 10 minus 8 is going to be 2. Okay. So we have 21 here. That's going to be, how many times does 21 go into, 4 go into 21? That's 5 times. So 5 times 4 is 20. 1, 2. Okay. So if you want to use the long division route, this is what you need to do. Okay. There's a 2. There's going to be an 8 here. Put a 3 down here. Okay. Does anyone see that? Okay. And we have remainder 2. So remainder 2. Okay. But if you want to use a shortcut, we can safely say since 16 is a power of 4, we can just say that we can use this notation. That this, that instead of using ones, instead of using 1 digit, we can use 2 digits to represent 16. Okay. Okay. So 32 in base 4 is gonna be, if we do this right, so 3 times 4 1 plus 2 times 4 0, that's gonna be, this is gonna be 12, this is gonna be 2, this is 14. Okay. And then if you follow that through again, so 10 to the 4 equals 1 times 4 to the first power plus 0 times 4 to the 0 power. That's going to look like 4. Okay? This is in base 10, okay? So we're not actually converting these in base 10, we're just using 2 bits or 2 digits to go from base 4 to base 16. Okay? So next 2 digits are 12. That's gonna be 1 times 4 times 4 to the first power plus 2 times 4 to the 0 power. That's gonna give us 6. Okay, so next 2 digits are 31 to base of 4, 3 times 4 times 1 plus 1 times 4 to the 0 power. That's gonna give us 13. Okay, and then the next 2 digits are going to be 23 to the 4th power, base of 4. So it can look like this if we resolve it to base 10. It's going to look like 11. Next 2 digits are 10 to the base of 4. It's going to look like this. That's 4. Okay, this is all in base 10. Okay, so to convert from base 10 to base 16, we need to know that I don't really memorize this, but I just use that A is going to be at 10 and then F is going to be at 15. So then A, B, C, D, E are the numbers that we use to represent 10 to 15, be 11, 12, 13, and 14. Okay, so this 14 corresponds to E, 4 is 4 in base 4, 6 in, 4 in base 16, 6 is 6 in base 16. 13 is going to be D, 11 is going to be B, and 4 is going to be 4 again. So remember, using this notation, this is going to be your most significant bit. This would be your least significant bit, okay? This goes at the end, or is that right? No, whoops. This will be your first. My mistake. It's because this is 32 corresponds to the most significant bit. This would be your most significant bit, not the other way around. So final result, if you want to put in base 16, it's going to look like E, 4, 6, D, B, and 4, base 16. Okay? Does that look good? So if you use the long array, you have to divide by 4 and figure out the remainder. If you use a shortcut, you can just see that the base 16 is a power of 4, because 4 to the 2 equals 16. You can just use the 2 digits to represent 16. Okay? So next math surprise is going to be, what does 2 to 2 look like? 2 to 2 is going to be 4. Okay? Okay. So we've done base conversions from 416. Let's try converting using the long way, but with a nicer number. Okay. So let's convert. Let's say 1101 base 2 to, I don't know, let's say base 8 to base 8, right? To do that, we have to do two things. We can have to convert this number into base 10. Let's not do base not 8, because it's a good part of 2. Let's just use base 9, okay? So we convert this number to base 10 and convert base 10 number to base 9, okay? To do that, we just do, you see that this corresponds to 2 to the 0, this corresponds to 2 to the 1, this corresponds to 2 to the 2, this corresponds to 2 to the 3rd, okay? This corresponds to 2 to the 4th. This is deasserted, so this does not hold any interest when we do conversions. So it's going to be 2 to the 5th. 2 to the 6th. This is 4, 5, 6, and this is 7. Okay. So an easy way, instead of using addition for all this, is to say that we can say that it's going to be, this number is going to look like 2 to the 8 minus this number, which is 2 to the 5th. Okay. So 2 to 8 is going to look like 256 minus 2 to the 5th is going to look like 32, right? Okay, so if we do subtraction, 256 minus 32 is going to look like 224, which should be this value. Okay, this is going to be base 10. Okay, so to convert this number to base 10 to base 9, we do the division route. So 224 divided by 9 is what number? So what does that look like? Let's use the long division route and see what it looks like. So this is 2, 18. It's gonna be 4. Carry this 4 down. 4 again. 8. So remainder 8. So it's 24 remainder 8. Okay, same thing when you do 24 divided by 9. That's going to be 2 remainder 6. And 2 divided by 9 is going to be 0 remainder 2. So the final result is going to be 2, 6, 8. That's going to be base in 9. Okay. Does it look good to everyone? Okay. So this is how we do conversions from base of 2 to base 9. We use base 10 as our intermediate base. Okay? Okay, so next topic is gonna be bitwise operations. So I wanted to do an operation, but before we do that, let's review over the operations to do. So there are around 4 operations that Dr. Zanaski has introduced to us, and that's the AND, the OR, the XOR, and the inverse. Okay? So for the AND, the truth table is going to look like this. That's the output. So for if AB is going to be 0, 0, it's going to be, the output is going to be 0. If the bits are 0, 1, 1, 0, or 1, 1, the output is going to be 0, 0, 1. So for AND, we need to have both the input to be 1 in order for the bit to be 1. Okay, this is for the AND. So okay, so for the OR, only one of the bits can be 1 for the result to be 1. Okay, so the same idea here. This is 0, 0, it means 0, 0, 1, it be 1, 1, 0, 1, and if both the bits are 1, it's going to remain 1. Okay, so for the inverse, for the XOR, it's going to be the exclusive OR, where it only says that only one of the bits can be 1 for the result to be 1. Okay, so XOR is going to look like this. So 0, 1, 1, 0. And for the NOT operator, it's going to look like this. It's unary, so you only use one operand. So we just invert the bit. Okay? That's our 4 bitwise operators, and how they are used to do fun and games on bits. Okay? So let's perform the operation on these 2 operands. To do bitwise, we need to convert these numbers into base 2. So using a shortcut, we can say that 1, 2, 3, 1, 2, 3, 1, 4. That this is going to look like 0, 1. As for 1, 2 is going to look like that. Okay, so 0, 2 in base 2. 0, 1 base 2 is 1 in base 4. Okay, so by that shortcut, we can say that 2, 3, 1, 4 in base 4 is going to be 1, 0, 1, 1, 0, 1, and 0, 0 in base 2. Okay, so okay, does everyone see that? Good? Okay, so then let's convert this number to base 2. Okay, so from left to right, we do 0, 0, 0, 0. It's a 3, so we do 2 1s. It's a 3 again. It's only 1. It's a 2. It's a 3, and then it's a 0, 0, right? So these are the corresponding bits. I'm just gonna write out the correspondence. It's gonna be easy to see them. Okay, so you want to add them. So it's gonna look like this. So 0, 0 gives us 0, 0, 1 gives us 0, 0, 1 gives us 0, 0, 0 gives us 0, 1, 1 gives us 1, 1, 1 gives us 1, 1, 0 gives us 0, 1, 1 gives us 1, 0, 1 gives us 0, 1, 0 gives us 0, 1, 1 gives us 1, 0, 1 gives us 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0 gives us 0. So this should be our final result in base 2. Okay, so if the question asks if we should put the answer in base 4, we can easily do that. And so converting this to base 4 will be just take the 2 bits and convert it to base 4 for each 2 bits. Okay, so this is going to look like 0, this is look like 0, this is going to look like 3, this is going to look like 1, this is going to look like 0, that's a 2, that's a 1, that's a 0. So our final result is going to be 0, 3, 1, 0, 2, 1, 0. That's base 4. Okay. Okay. So does that look alright to you? Okay. So, and then for the math surprise, it asks us what is 2 to the power 4? That's going to look like 16. Okay. Does that look good? Okay. So for our next topic, I want to go over base backtracking. And so far, we've seen backtracking used in which algorithms? We've seen that it's used for doing the n queen problems, or you have a board of size n, and you want to figure out how to put the queens so that they won't attack each other, right? So we looked at the first column, we put it here, and then we made our recursive call, and it's gonna look like this. And then we put the queen in the next column at row 1, and we check if this state is a good state where the queens are unable to attack each other. If they do attack each other, we return to our previous state and make a new recursive call. Okay, because these queens attack each other horizontally, we go back and we go back into our previous call. Okay, so then we insert a new state, and then so new state was going to look like at row 2, then at column 2, then row 2, which is going to look like here. Okay, which is here. But then this state is also a bad state because these queens can attack each other. Okay, so we turn back, and then and then we keep going down on this path for this one queen. Okay. Okay, we said that this state works because these 2 queens can't attack each other, so we keep going down. We could keep going down on this path. Okay, and then on to the next new column. Okay, but because this state is bad, it's not good. That these 2 queens can't attack each other, we return back. Okay. And we keep going down our recursive descent and try to see what states can all the queens be safe in. Okay. Okay. Is everyone good with the n queens problem? Okay, that's one way where we've seen backtracking used. The next problem is the fox, the goose, bag of beans, and the farmer. Okay. So with this problem is from our family of problems known as the river crossing problem, where there's a river, and then there's a farmer, there's a fox, there's a goose, and a bag of beans. Okay. He wants to go cross the river in a boat, but the boat fits only 2 items: the farmer and one of the items. Okay. So bad states in the end queen problems. The bad states were where the queens can't touch each other. In the fox, goose, the bag of beans problems, the bad states are where the fox and the goose are on one side of each other without the farmer, at least to death. And next is the goose and the beans. The goose can eat the beans, and that's not good. But the fox and the beans are okay. The fox doesn't want to eat the beans. Okay. So we just using a backtracking, we can solve how the fox, the goose, the bag of beans, and the fox can get to the across the river in one piece without hitting any of these cases. Okay. Okay. So to do that, right, we can keep going on this path. So this is our beginning state where the top represents the top side of the river, the bottom represents the bottom side of the river, and we can just keep changing our states. So we generate our possible moves, and we just change our states and check if if the state is valid or not. Okay. So we go to state 1, where the farmer takes the goose with him, and see that this is a good state, that we have not seen this state before, and this state is valid. It won't lead to death. So you keep going onto this path, and we say that the farmer goes across the river, leaving the goose behind. And then we can take which one anyone will do. We can take the fox with him, leaving the beans behind. The farmer goes to the south with the fox and the goose, and then we can then we keep calling our recursive descent into this path, and then we can take either the fox, the goose, or nothing home, or nothing to the top side, and we just go to you could just pick any one of these states. So say let's pick the goose with him. So farmer brings the goose along to the top, leaving the fox to the south, and then we keep going and just finding our path. So the farmer is going to bring with him the bag of beans, leaving the goose behind. Okay. So we keep going down here, keep going down, then we keep calling our recursive descent. Okay, so the farmer leaves the beans and the fox together at the south side, and only takes himself to the top of the goose. And then next recursive call will show that the fox, the goose, the bag of beans, and the farmer are all safely at the bottom side. Okay, so this is how we use backtracking in the fox, goose, bag of beans, and the farmer problem. It's also the maze we've seen, where we have a maze, we want to escape from the maze by going to any direction at all possible, from left, right, bottom, and top. You go up, down, left, right, making one move at a time and just brute force our way out of the maze. Okay, so with the maze, say we're here and exit here, right? We can go up, left, right, or down. Okay, so we just make a move, check that it's a valid move to make. Then we call our recursive function on ourselves onto new move and see that if that state solves the problem. If not, we keep going onto that path. Okay, that's for the maze problem. Okay, is everyone fine with that? Okay, so that's some of the algorithms that we've seen backtracking use. There's solve for n queens, the fox, the goose, the bag of beans, and the farmer problem in the maze. We also seen backtracking use in trees, right? So in a binary tree, let's say we have a tree here, right? And then if you want to say print out all of these values in the tree, we can use a backtracking algorithm that goes to the leftmost, the bottommost level and print it off. So we go here, print off here, and go back and print. Then we go over this subtree and print. Then we go back to this area, this node here, print off, and print off here. Then go back to the root and print off. Okay, so that's kind of like a backtracking where we change our state and then say that if it's a valid state to make, that say if the state has not been seen before and or the state actually exists is not null. Okay, so let's go and talk about the anatomy of the backtracking problem of the algorithm and see what are some common features found in backtracking algorithms. So for one, we need to have our base case because backtracking is a recursive function. So in our base case, to check if we've solved our problem. If not, keep going. Then this is kind of like a base case, but we need to check for duplicates. Check if this is a state we've seen before. Okay. And then after we've done our base case and we check that it's a valid, or if it's not a state we've seen before, we can do our, we can generate a list of possible moves to make. So, and see how we can solve our problem. Okay, so in our, usually we have a for loop, increasing I or somehow changing the state of our problem. Okay, and when we generate possible new moves, we check that if the move's valid or not. Okay, and then we make the change. If it's a valid move, if it's valid, we make the change. Make this change of the state. Change the state. And then next, once we change the state, we call our recursive function on the state and see if the case is successful. Then we accomplish our goal. If not, we keep going down our recursive descent. Okay, so perform the recursive descent. It's okay. Then next, this is optional because sometimes we don't need to we don't have to process a return value, because like for these cases, the maze and fox goose bag of beans, we just wanted to return when we succeeded. When the fox, goose, bag of beans reached the south side of the river, and for the maize, when we reached the exit, there wasn't any value to return besides true or false. But for the queen's problem, we wanted to know how many states allowed for some variable number of columns and rows that allow for the queens to be safe. How many states were found in an n by n chessboard? Okay, so with the n queens problem, we had to process the return value of the state, of the successful state. So optionally we should process the return value of the recursive call. Okay, and then next, once we change the state, we want to undo the state change. Okay, I will explain that in a moment. So for the maze problem, if our guy was here, and if we went down, and we see that wasn't a valid move to make, or that was a duplicate, or we've reached a duplicate state, we want to go back and not keep going on this path. So we want to track back. This is where the backtracking name comes from. Okay, so if we don't undo our state, we will always keep going down, 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 instead of going to a new state, which is here. Okay, does that make sense? Does everyone have a good idea of backtracking? Okay, so the math prize that I have planned for this question is, what is 2 to the power of 0? And 2 to the power of 0 is going to be 1. Okay? Okay, so that's all I have for backtracking. Okay. So I see that we have about an hour left. Let's look at any more topics we can look at further. So let's talk about binary trees and what are the structure of some trees. Okay. Okay. So binary trees. Okay. So we have 3 different naming schemes for a tree. You can say a tree is complete when all the levels of a tree are filled except the last level. So for a complete tree, this can be a complete tree. So when level, I guess this is level 0 is filled, level 1 filled, but the last level is not filled because these are empty leaf nodes. So this is a complete tree. But if our tree looks like this is not a complete tree because this guy here needs to be filled up. Okay? So, and there's also a tree called a full tree. So a tree is full when every node in the tree has at least 0 or 2 children. Okay? So when every node has 0 or 2 children. So this again, if we do this, this is a full tree. But if we do this, this is not a full tree because this parent node has only 1 child. It only should have 0 or 2 children. Okay. So it needs to have at least a guy here, or we just kill off this guy to make it a full tree. Okay, and then there's a perfect tree, which is a combination of the complete and full tree. So the perfect tree says that it's where all the non-leaf nodes have 2 children and all leaf nodes are on the same level within the tree. Okay, an example of that is gonna be this thing. So this is an example of a perfect tree. Okay, so a tree that's not perfect can be either this or, wait, is that a perfect tree though? So I think it's just this thing. That's not perfect tree, because this guy can have a child here. Okay, and even this guy can have a child here. These are not perfect trees. Okay. Okay, so let's talk about the height of a complete binary tree with n nodes. How do we describe the height of a complete binary tree with n nodes? So let's say we have a complete tree. Let's say this is our example, right? So this is our complete tree, and it has 1, 2, 3, 4, 5 nodes. How do we say the height is? Height is gonna be this is the height, right? So height's gonna be around 1 and 2. Okay, so to say that the height generally is gonna be the floor of log of 2, log base 2 of n, where n is the number of trees we have. So if we do the floor of the log, so the log of 2 of 5 is gonna be around 2 something. And we floor it, right? We truncate it down, so we remove the decimal numbers away and get 2. So height is 2. This equation will allow us to describe the height of a complete binary tree with n nodes. Okay, so that's what I have for binary trees. If we're all clear with that, let's look at more heaps problems. Okay. So, okay, let me just organize more. Okay, look good. Okay, so heaps. Okay, for heaps, it has 2 properties, which are the structural property and the ordering property. So for the structural property, it needs to be a complete binary tree. For ordering property, it depends on what kind of heap it is. For a min heap, the parent node must be less than or equal to its child, and for a max heap, the parent node must be greater than or equal to its child. Okay, so for min heap, we want the root to be the minimum value. For max heap, we want the root to be the greatest value. Okay, so for heaps, we have 2 operations we can use, and they are the delete min and the insert operation. Okay, so there are 2 operations, which is delete min and insert. So, but what about if we can a question to ask is, if we can delete the min, can we delete any value in the heap? The answer is no, because the heap only has two properties, the structural and ordering. If we want to say this is 20 is our root, we want to delete 25. We do not know if 25 is going to be the left child or the right child, so we can't delete any arbitrary number in our heap, only the minimum or the maximum, depending if you use a min heap or max heap. Okay. Okay, so I did a insertion from a min heap. Let's try doing deletion for a min heap. Okay, so example of a min heap, I'll just make one. Let's say this is gonna be 30, 29. Okay, so let's call delete min on this guy and see what happens. So if we delete min, it's gonna we take out the root, replace it with the leaf node. Okay, so if we call delete min, it's gonna look like this on the first go around. Okay, so then we need to restore its heapiness, where the structuring property and the ordering property of this heap must hold. When we set that the root, that this guy is greater than 30, 29, which is our children. We want the root. Oops, can't do that. So we want the root to be less than its children. So you can either take 30 or 29. So the number to take would be 29. You want to take the number that's less than either of the two. Okay? So we call percolate down on 35. We should get this as our final result. Okay. Okay, so that's the delete min operation for a min heap. Okay, any questions on that? Any questions at all? Okay, so let's talk about how to represent a heap in an array and what are the equations for that. Okay. So if we have a heap, so I'm gonna make a random heap. 1, 2, 3, 4, 5. Right. How do we represent this heap into an array? Okay. Well, we can call min heap. We can call delete min and just insert as you go and say 1 is here. Then we call and then we after calling delete min, we need to delete min actually. So you gotta delete this. So it's gonna look like we take the rightmost leaf and we swap it with the root. So it'll be here. This is what it looks like after the first go around. Then we call down percolate down, and 2 moves up, 5 moves down. We keep calling percolate down on 5 until this heap has been reached heapiness. Okay. Okay, then if we delete, could we call delete min again, 2 pops out. And then, well, 5 gets swapped at the root. Okay. Okay, so to store heapiness, we want to call percolate down on 5, and it's going to look like this. Oh, okay, and that's the result of calling down percolate down on 5. 3 gets swapped with 5. Then we call percolate down again. We call delete min, and we see that 3 is the root. Then we delete 3. It's going to look like, and then we take the rightmost leaf node and we swap it with the root. Then we call percolate down on 5 and see that 4 is smaller, so they swap. And then we call delete min to represent the heap into an array. And then we get 5 as our last remaining value, and there. This is how we represent a heap into an array by calling delete min on it. Okay. So some equations to keep in mind if you want to go back from array to heap. So for heap to array, we do delete min, but for array to heap, we need to have these equations in mind. So the parent of a node of at I will look like I minus 1 divided by 2. The left child of I will be I times 2 plus 1. Okay. Then for the right child, it's going to look like this. I times 2 plus 2. Okay. We see that these equations hold because if we represent the heap as, say, this is index 0, index 1, 2, 3, 4, right? 0, 1, 2, 3, 4. The parent of 2, let's say, if we insert node 1, the index of node 1 into here, it's going to be 1 minus 1 is 0 divided by 2, that's 0. So the parent of this guy should be this guy, which this equation holds. If you do it on here, on this right child, we see that 2 minus 1 is 1 divided by 2. 1 divided by 2 is going to be 0.5, but we truncated it down in C to 0, which this equation holds true. So if you go to the left child of I, let's say for this guy, for the root, put 0 here. 0 times 2 is 0, plus 1, it's here. Okay? So this equation holds true for the left child, but for the right child, we've say that the right child of the root at 0 is, we've insert 0 here, times 2. So we 0 times 2 is 0, plus 2, it's here. So right child is here. So these equations hold for the root. Okay? Does anyone see that? Is that good? Okay. So that's what I have for chasing through operations for a heap and array. Let's look at an application of heaps. That's going to be heap sort. So what is this? Okay. Okay, so let's look at heap sort. Okay, so heap sort uses heaps to put the elements into an array. It's like what we did with the array representation, where we can sort a data structure using heaps and putting those heaps into an array. Okay. Okay. So if we want to insert an element, the big O runtime for that will look something like big O n log n, right? Because we have n elements and we have to insert. Worst case we insert, it will be log of n. Okay. This is for inserting n elements into an array from a heap. If we delete all elements, that will also be big O n log n. Okay. So if we print them, if we delete the elements from a heap, it will take n times log n runtime. Okay. Is everyone clear on heap sort? Okay. Okay. So we've done tries, we've done the binary trees, we've done heaps. Let's return to hash tables and see what makes a good hash function. Okay? Hash functions. And see. So first off, we want our hash function to be deterministic. Deterministic means that we have a one-to-one I want to say a one-to-one representation of our input to the output. Okay. So the value, let's say our input's gonna be 1, 2, and 3, and then it just means that 1, 2, and 3 should not have the same output. They should be unique. Okay, like A, B, C, right? So 1 goes to A, 2 goes to B, and 3 goes to C. They should not have the same output. Okay. Next, the hash function should use all the input data. If the hash function does not, or is not able to use the input data, it will not be useful to us. Okay. So next thing to know for a hash function is that the hash function should uniformly distribute the data across the entire set of possible hash values, right? Because you don't want collisions in our hash table rather than ordered n runtime, which is worst case. Okay. Okay. So for deletion in a hash table, when we delete, we don't fully delete. We have a flag to represent if the index has been seen before or if has been used before, or if the index has not been used before ever. This flag is sometimes called a dirty bit. it helps the algorithm determine if it can stop or keep going when it does retrieval or lookup. Okay. And next thing to go on is when the hash table gets too full and we decide to expand it. Okay, so usually we expand our table dynamically, meaning as it fills up, we expand it. So when it reaches 50% capacity, we would like to expand it and rehash all the values that were already in the hash table. If we don't rehash them and leave it where they were, when we try to retrieve it, we will not actually retrieve the value, because we use the table size in our hash function. Okay. So for linear and quadratic probing, we want to expand when it's 50% full, and we want the table size to be a prime number for quadratic probing. This helps ensure that we will never, at least hopefully never, run indefinitely when inserting. Okay, but for separate chaining, we don't need to insert. We don't need to expand when it's 50% full. Usually, we want to expand when the number of elements in the table is approximately equal to the number of linked lists being maintained. That just means that we want the size of our elements to be around. We want the size of the table to be around the size of the elements being inserted. Okay. Okay. So that's what I have for hash tables. So I guess the next thing to do is let's go to bitwise operations. And I haven't talked about shifting at all. So bitwise operations and bit shifting. Okay. So when we do the right shift, depending on if it's a signed int or unsigned, we can either put a 0 or a 1. Okay. For a signed int, we copy the most significant bit. For example, right? It's gonna be 1, 0, 0, and then let's say this is the 31st or 32nd bit. That's right there. That's the signed bit, and it's gonna be all zeros. This is our first bit. Okay, this bit determines whether we pad with 0 or 1. So if we do this and we do right shift by 1, we have to insert or pad with 1. Okay, so this was the original. This was the added in. Okay, but if it was unsigned, we don't need to pad with a 0, pad with a 1. We can just put a 0 there. Okay, so we do 1, put a 0 here, because this bit is not signed. Okay, does that make sense? So for signed bit, the range of numbers is going to be around 2 to the power to negative 231st, all the way through 2 to the 31st minus 1. Okay, so this is the negative numbers. This is the positive range of numbers, okay? Okay, this is for sine, but for unsigned, the range number is going to be from 0 all the way to 2 to the 31st. Oops, sorry, a second. Minus 1. Okay. 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 We can't see that. Okay. Does that look at the if one for bitwise operations? Okay, this is for right shifting. For left shifting, we do, regardless of whether it's signed or unsigned, we pad with a 0. Okay. So if, for example, here, right, our previous example, right, we use 1100 all the way to 00. If you want to shift it by 1, it's going to look like this. 1000. So this is the extra one. This was the original number, but this fell off. Okay. So regardless of whether if it's signed or unsigned, we can just pad with a 0 when we do left shifting. But it's important to remember though, when you do right shifting, we need to know whether the int is signed or unsigned. Okay. Okay. So. Okay. So I think that's what I have for bitwise operations. We've looked over the AND, the OR, the XOR, the inverse. We looked at left shifting, right shifting. Is there any other operations left to do? Or we want to do more examples? Okay. 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 So I think I have an example of recursive. Not yet. We have like half an hour left. Okay, so I have an example of recurrence relationships. And let's go over one example before I leave. Okay. Okay. So as an example, let's say you have t of 0 is a constant and t of n is going to be t of n minus 1 plus t of n minus 1 plus c1. For our boundary, we have n is greater than 0, okay? And now I want to know what is the big O runtime for this function, okay? So to do that, you can see that, let's try simplifying this equation. We see that t of n, I need some padding room. Okay, so we see that t of n, these two are the same. It's going to be t of 2 times t of n plus c1, okay? then when we insert this number into this function, we get t of n minus 1 equals to 2 times t of n minus 1 minus 1. So then we do plus c1 again, okay? So this guy will look like 2 times t of n minus 2 plus c1, okay? So usually we want to do around 2 to 3, maybe more iterations and see if there's a pattern or a pattern for us, a pattern for this recursive relations problem. Okay. Okay, so let's do another one. So t of n minus 2 equals 2 times t of n minus 2 minus 1. Okay, so that will give us 2 to the t of n minus 3 plus c1. Okay, so we went through 1, 2. Let's do another one. Make sure we found a pattern. So if you want to simplify this down, it's going to be 2 times t of n minus 4 plus c1, okay? So when we do this, we have to put all these equations back into the initial equation, which is here, okay? Okay, so shows that t of n looks like, so remember this is our first iteration, second, third, and the fourth. Okay, so if we put all this back, it's gonna look like this. So it's gonna be 2 times t of n minus 1, which is this guy, which is going to be 2 times, which is this guy here, this guy, 2 times t of n minus 3, which is this guy here, 2 times t of n minus 4. We add in the plus c. We add in the plus, we go back here, we add in the plus c here. Go back here, we add in plus c1. Then we go back here, we add in plus c1, okay? So that should be what, if we put back all our equations back into our initial equation, it's gonna look like this. So you have, we see that we have 2 to 4 t n minus 4 plus 4c1, okay? So this is for if we done 4 iterations of the initial equation, okay? Okay, so we see that this guy is looking like a summation problem. Okay, and this guy is just itself. Okay, so if we want to put this in terms of k, we can say that this guy is going to be 2 of k times t of n minus k plus the summation of, oh wait, I didn't. So it's this whole chunk that goes through that guy. So I gotta do this thing, this thing. Oh man, that's not that. So it's gonna be like, it's just gonna look like a bit. It's gonna look like. So it's gonna look like C1 plus 2 times C1 plus 4 times. So this is itself times 2 times 4 C1 plus 8 C1, which is about k minus 1 from I to 0. This is going to be 2 to I C1. Okay. Okay. Anyone fine with that? Okay, so you want to solve for this geometric sum. Okay. 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 So I'm gonna use a different paper to solve for that sum. Okay. Okay. So let me say that S equals to okay. And then if we use Doctor's Zernetsky's method, where we iterate due to I, so on the first, when I equals 0, it will look like this. And well, we can just put this guy, can factor out C1 to put it here. Okay, so that we won't have to write C1 every time. Okay, so it's gonna look like 2 to the 0 plus 2 to the 1 and 2 to the 2 all the way to 2 to the k minus 1. So with geometric sums, we want to multiply S by the coefficient of whatever I is being the exponent of. Okay, so 2 times S is going to look like, so this guy's going to look like 2 to the first plus 2 to the second, then plus 2 to the third, plus all the way to 2 to the k. Okay, so this is for S, this is for 2S. Okay, so one more time. So if we want to find out what S is, we should subtract one from the other, and we can see that if we do subtract 2S minus S, we get this number and this number. So if we do zap, 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 and zap, zap, we get 2 to the k minus 2 to the 0, which if we simplify it down, it's going to be S equals 2 to the k minus 1. Okay. Does that look good? Okay. Okay. So having done this summation problem, we've resolved the summation to a equation. Instead of a summation, we can put this equation into the summation and replace that. Okay, so if we do this right, it's gonna look like, so T of n will look like something around T of k from T to n minus k plus C1 and T of k minus 1. Okay. Okay. So we want to remove the k's and get our T of n equation into a function of n, not k. So we know that from a base case, right, that T of 0 gives us C2. So let's try to make this guy become 0. To make this be 0, right, and if k equals 0, that gives us n equals k. So if we see a k, we put an n there, okay? So then our new equation will become 2 to the n 0 plus c1 times 2 to the n minus 1. Okay, does anyone see that? Okay. Okay. So let's try to resolve t of 0 and make this more simplified. So t of n is c2 plus t of n c1, then minus c1. Okay. And if we do the big O of this guy here, we see that big O is going to be 2 to the n. We drop the constants and we left with 2 to the n times a constant plus 2 to the n times a constant, which is just big O 2 to the n. Okay. Okay. Okay, so we have around 12 to 15 minutes of time left. Are there any questions for any other topics? Or do you think we've done a good job at reviewing for CS1 for your exam on Friday? Okay, so let's just reiterate what we've gone through, and hopefully that's still in your mind on Friday. Okay. Okay. So we've talked about tries, and when to insert, lookup, and delete. What are runtimes for inserting? Worst case can be ordered at k, where we go through all the letters in the string to insert into the try. The best case, it's going to be order k again, because we have no way of stopping. You have to keep going and go through all the letters in the string. For lookup, the worst case is going to be order k. We have to look up all the letters in the string, but if the best case, order 1. When the string is not even in our try, we can just go on the first letter and say if z is in a try, let's say this try, it's zoology in this try, we go to z and it's not there, order 1, look up. For best case. For deletion, it's going to be the same thing as our lookup, order k. If we want to delete a string that's in our try, and best case, order 1 if the string is not even in our try. Okay? But the one thing you should not assume is that the try is small. Like in our example, we have 6 words or 6 strings in our try. We should assume that our try is arbitrarily large, that there's an infinite number of, it's a very, not infinite, but a very large number of already established elements into our try. Okay, guys? So remember that. Don't fall for the trap. Okay. Also, be sure to know your power of 2s, because when you need to do some bitwise operations, do some AND, ORs, XORs, and inverses, power of 2 are helpful. Okay. So we've looked at heaps. What we talked about was a min heap. When they have the structure property of being a complete binary tree. We've also talked about their ordering property, where every node has a value less than or equal to all values in a subtree. Okay. We talked about inserting into a min heap. We also talked about deleting from a min heap, where we need to call percolate down every time we've put the rightmost leaf node at the root. Okay. So we talked about conversions from base 4 to base 16. We can convert from base 4 to base 10 to base 16, or we can use a shortcut to convert from an easier method. Okay. So we talked about hash tables. What's on a bigger runtime for linear probing, quadratic probing, and separate chaining. Each of them has their own niches, so you should know when to insert at what index for each collision resolution policy. Okay. Also know that when you want to insert at a hash table using separate chaining, we want to insert at the head because of temporal locality. It says that data that's used recently will most likely be used again. Okay. Okay. And then we talked about performing the AND operation on two numbers. Remember, for the ANDs and ORs and the bitwise operations, the numbers should be in binary notation. They shouldn't be in their decimal, their octal, or the hex, or any other basis. We need to use bits for bitwise operations. Okay? Okay. Then we talked about backtracking, how it's used in Queen's problems, the maze, and the farmer, the fox, the bag of beans, and the goose. Okay, we talked about the anatomy of a backtracking algorithm, where we need to have our base case. We need to check for duplicate states. And then we generate our possible moves. We check if the move is valid, and then we make the change to the state, and then we perform our recursive descent. As an option, we need to process the return value of the return value of the recursive call, because for n queens, we wanted to know how many possible board states there are for a n by n board. But for fox, the farmer, the bag of beans, and the goose, we didn't care if there were 10 million, one. We care if there were only one state only. We return true on that case. For the maze, same thing. We only want to know at what route if it was possible to escape from the maze. Okay. Okay. So I think that does it for time. I want to thank you for coming here at the morning of 9:30 on a Tuesday, December 5th. Okay, awesome. All right. So I'll be staying here for a while after the review to answer any more questions you have.